Okay, so today we're going to start a new section in our notes, namely section 8, I guess, section about cardinal numbers. Yes? Next Wednesday. So I'm going to send an email about that, don't worry about the exam today probably. Anyway, so the motivation behind ordinal numbers was that we wanted to find sets which represent ordered types of valued sets. Okay, I may be lying, maybe I didn't give this as the motivation, but once we learned about ordinal numbers, and you learned that ordinal numbers represent ordered types of strictly well-ordered sets. Okay, so ordinal numbers are supposed to represent strictly well-ordered sets. We want cardinal numbers to represent equinumericity classes of sets. What do I mean by that? Two sets are either equinumerous or not. They're equinumerous if there's a bijection between them, if they're of the same size. Otherwise, they're not equinumerous. Now, pretend that you take all the sets together which are equinumerous to each other and put them in a giant collection. I would call this an equinumericity class. I want to represent these. In other words, I want to represent sizes of sets. I want to I want to be able to name the sizes of sets. Cardinal numbers are supposed to capture this. And in the past, before the von Neumann definition of ordinal numbers, people defined cardinal numbers as follows. They took all the sets together which are equinumerous to each other, and they put all these sets in a single class, and they called this a cardinal number. We could have worked with this if we were living in early 1900s, but we don't do this because that brings us technical difficulties, like we have to deal with proper classes and so on. It turns out that using ordinal numbers, you can define cardinal numbers in a very smart way. We're going to call an ordinal number which is not equinumerous with previous ordinal numbers a cardinal number. And then the following question will arise. Is every set equinumerous with a cardinal number? In order to be able to make this jump, we have to prove that every set can be put in a bijection with an ordinal. How can you prove that? How can you prove that any set can be put in a bijection with some ordinal? There's no easy way to do this, and it turns out that you need the axiom of choice or some variant to prove this. What we're going to prove today is that every set can be well-ordered, and from this it will follow that every set can be put in a bijection with an ordinal. Why? You take a set, you well-order it, now it's isomorphic to some ordinal, therefore it's in a bijection with some ordinal. And then it will be in a bijection with some cardinal number, which will be called its cardinality. So this is basically our roadmap, and we're going to first prove that every set can be well-ordered, and in order to do that, we're going to need something called Zorn's lemma, okay? So let me state Zorn's lemma. Let's say that we have a partially ordered set such that every chain has an upper bound in P. Now I'm going to explain what this is, and let me explain what this word means. That is, for every subset C, if elements of C are comparable, then there exists some P such that P is greater than or equal to all elements of C. Now, if you have such a partially ordered set, the conclusion is that there exists a maximal element. Then there exists, you see, I didn't say greatest because we're working in a partially ordered set, not necessarily a linearly ordered set. There exists a maximal element in this partially ordered set with respect to this order relation. So in order to apply, this is called Zorn's lemma. In order to apply Zorn's lemma, you need a special kind of partially ordered set, a partially ordered set where every chain has an upper bound. Now, what does this word mean, chain? We did not define this as far as I remember. It's in the notes, but I may not have mentioned this. A chain in a partially ordered set simply means a linearly ordered subset. In other words, a chain is a subset where any two elements are comparable, okay? Now, you want every chain to have an upper bound. What this means is that you want to have some element in this partially ordered set which is greater than or equal to every element in this chain. And you want this to be true for all chains. Okay? You want this to be true for all chains. So if every chain has an upper bound, then there exists a maximal element. Okay? This is Zorn's lemma. Now we're going to prove this. And the proof will start by assuming the contrary. Okay, let's take such a partially ordered set. Let P be such a partially ordered set. And assume that the conclusion is false. Assume that P does not have a maximal element. Then for every chain C, the set U sub C consisting of elements in P such that this happens is non-empty. Yes. Okay? Now, why is this true? Because, okay, here's the claim. For every chain, this set is non-empty. Here is why this is true. Take a chain. My partial order satisfies the requirements of Zorn's lemma, meaning that every chain has an upper bound. Okay? So this chain has an upper bound. There exists some element which is greater than or equal to every element in this chain. Now this element is either inside C or outside C. Because, okay, and I assume that there are no maximal elements in this P. I assume to the contrary that P does not have a maximal element. which means that this guy cannot be in C. Well, okay, it can be in C actually. I mean, it can be in C, but the point is this guy cannot be non-empty. Because if this were non-empty, then that upper bound would have to be in C, and it would be a maximal element. Okay? The point is when you assume two facts together, that this guy has an upper bound and there are no maximal elements, you can always find some element which is greater than all elements of this chain. Okay? And that will have to be by definition outside C. What do you mean? A chain is a single subset. This P, I'm not saying that, what do you mean? When I say every chain is an upper bound, those upper bounds may be different. I'm not saying that there's a single upper bound. Every chain has its own upper bound. Sure. No, a chain by definition, it's a linearly ordered subset. Every elements are comparable in a chain. So I have a chain. These are comparable. I assume that there is some upper bound. Okay. I assume that there are no maximal elements. Okay. Which means that there is something greater than this. There is something greater than this, and so on. And these guys are necessarily not in this chain. Now, these sets are non-empty for every chain. Using the axiom of choice, or a consequence of axiom of choice really, I should say using because the actual statement does not imply this directly. Using the axiom of choice, one can find a function f from set of all chains. Okay, let this be denote the set of all chains in P to P such that f of C is strictly greater than C for every C in C. Now there are too many C's on the board. Let me explain. These guys are non-empty, so by axiom of choice, I can choose one element from each of these guys. Okay? There exists a function which chooses one element from each of these guys. How does that function behave? When you input a chain into that function, it chooses one element from this guy. So the element it chooses is strictly greater than all the elements of the chain. Okay? So axiom of choice is really applied to the collection of all these sets. These sets are non-empty. I choose one element from each of those. I name the function which chooses one element from each of those guys f. For each chain, I choose one element in my partial order which is strictly greater than every element over there. Okay, there is such a function. The existence of this function is guaranteed by this assumption that P does not have a maximal element and that every chain is an upper bound. Now, fix some element of P, okay? I mean, I'm dealing with a non-empty partial order because there is supposed to be some element in P by the assumption. By the assumption, I'm working with a non-empty partial order. Fix some element. Now, here is the crucial part. By transfinite recursion, define the following sequence, the transfinite sequence. I'm going to do recursion. Here's what I do. In order to pick the alpha element, I look at the elements I have chosen so far. If these guys form a chain, then I apply f to this. And otherwise, I define a sub alpha to be a sub 0, okay? So, and let's make sure that alpha is not 0, okay? The set of all non-empty chains. I mean, empty set, every element of empty set is comparable, so it's a chain, but I don't want to include that because I can't choose one element from this guy. So these are supposed to be non-empty. Anyway, here's what I do. I start with A0. Then I ask myself the following question. Is A0, the set A0 is a chain? Yes, it is. So I choose one element which is greater than A0. It's, let's say, I'm going to call it A1. Now I look at A0 and A1. Is this a chain? Yes, because A1 is supposed to be strictly greater than A0, so they're comparable. Now A0, A1 is a chain, so A2 is supposed to be some element greater than those. So I keep choosing elements. Now, it is easily shown, this means that I'm not going to prove it, that it's easily shown by transfinite induction that if you apply by a transfinite induction argument, you can show that we are always in this first case, okay? I just defined this as the definition is piecewise, but a transfinite induction argument shows that we are always in the first case. And consequently, the following happens. We're always in the first case, so if you have beta less than alpha, a sub beta is strictly less than a sub alpha because this is defined to be f of this guy. So f picks one element which is greater than all these guys, strictly greater than all these guys, so this is true. So what you need to do here is, which I'm not going to do, just show by transfinite induction that we are always in the first case. Consequently, the following happens. Okay? Thus, from every ordinal, now I have the following sequence. Let me draw the picture. I have A0, I have A1, I have A2. These are picked by f. Let me do it like this. This is a chain, so by definition, A1 is f of this set. It gives me some A1. So I apply f to this chain, I get A2. I apply f to this chain, I get A3. And I can continue this through all ordinals. This chain this is just indexed by ordinals. By transfinite recursion, I can do this. Now, from every ordinal, omega, we found a function, we found an injective function from omega to p, namely, gamma goes to a sub gamma. Look at the function which sends gamma to a sub gamma. Because my sequence looks like this will be an injective function. But as you can see, I just showed that there exists a function from every ordinal to p. Just cut this at omega. This is an injective function. 0 goes to this, 1 goes to this, gamma goes to a sub gamma. This is an injective function from this ordinal to my set p. but this is true for all ordinals. So from all ordinal, like for each ordinal, I can find an injective function from that ordinal to my set. This contradicts the existence of Hartog's number. For every set, there is supposed to be an ordinal from which there is no injective function to your set. This contradicts the existence of the Hartog's number of P. Okay? So the idea of the proof is easy. If you just assume that for every chain you can find something which is strictly greater than everything in that chain, you can just pick elements transfinitely. You just keep picking elements. This is a chain, pick some element. 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 You can do this transfinitely. But then the number of elements in P, like you found basically an injective mapping from the class of all ordinals to P, which is a contradiction. Okay? Because you know that there is supposed to be some ordinal from which there is no injection to P, namely the Hartog's number. Like the least such ordinal is called the Hartog's number. Okay? Okay? So this is a contradiction. The contradiction arises because I assume that P does not have a maximal element. Questions about this? So no questions about Zorn's lemma. Good. Let's continue. Let's prove using Zorn's lemma that every set can be well ordered. Now, in this proof, I'm not going to directly use the axiom of choice. I'm just going to use Zorn's lemma together with other axioms of ZFC. So I'm just going to write this down. There's a reason I'm specifying this, which you'll see in a sec, which you'll see in like 20 minutes. So we're going to prove the well-ordered ring theorem. This is known as the well-ordered ring theorem, which says that every set can be well ordered, meaning that for every set I can find a well ordered relation on that set. Now the proof of this, as you can see, we'll use Zorn's lemma. In order to use Zorn's lemma, we have to have some partial order where every chain has an upper bound. So let me create a partial order. So let's A be a set. Consider the following set P, which consists of tuples B and some relation such that B is a subset of A, and this relation is a well-ordered relation on B. Okay? So I start with a set. I look at the set of all tuples of the following form. I have a subset of A, and I have some well-ordered relation on this set. Define the following relation on P. I don't know how to pronounce this. What should we call this? I don't know. Define this, I'm not going to call this anything. I'm just going to avoid calling this by some name. Define a relation on P as follows. Given two such guys, two such tuples, one of them is related to the other. Okay, I'm going to call this square subset because it looks like a subset and it's like it has corners. So this tuple is square subset related to this if and only if the following happens. you want B to be a subset of C. You want this relation to be a subset of the other relation. And you want B to be an initial segment of C in the second well-ordered ring. Okay? So I take two such tuples. I say that one of them is related to the other if this guy is an initial segment of C in this partial ordered ring, B is a subset of C, and this relation is a subset of this relation. Now, little exercise. P is a partial order. P together with this relation is a partial order. Which set is, well, okay, why is this a partial order? It's obvious that this is reflexive, and transitivity should be obvious as well. Like, pretend that there is some D such that this is related to D less than or equal to D. And then you want to show that B is a subset of D, this relation is a subset of less than or equal to D. Those will be automatically satisfied. The only part you have to think just a bit is the following. If B is an initial segment of C in this relation, if C is an initial segment of D in the other relation, is B an initial segment of D in less than or equal to D relation. And it's easy to show that this is actually true. So this is transitive as well. Antisymmetry is not difficult to prove, so you can do this. Now I'm trying to decide whether I should leave this exercise as is or I should assign the next part to you as well. Okay. I'm not going to assign the next part as an exercise. I want to say some words about this. So this is a partial order. We claim that this partial order satisfies the hypothesis of Zorn's lemma. So what do I need to show? I need to show that every chain has an upper bound. Okay? So let C be a chain. Say this chain I chose, well, its elements are of this form. They're well-ordered sets, so let me index them as follows. Say C is this for some indexed families A sub alpha and less than or equal to A sub alpha. Okay, let's pick a chain. This chain need not be countable. It can be uncountable. It's some subset. So its elements are of this form because that's how my partial order is constructed, right? Its elements are well-ordered sets. So let me index their elements like this. Let me name their elements. Then, if you take the union of these guys, and if you take the union of these guys, this is an upper bound for C. And this is an element of, is an upper bound for C and S and P. Now, prove this is an exercise. Again, this part is an exercise as well. If you just take a chain like this, if you take the union of these first components, this would be the underlying set of your well-ordered set. And if you take the union of these relations, this union will be a well-ordered relation on this union. And moreover, because of the way I defined this square subset relation, this would be less than or equal to this guy, okay? This would be related to this. This is easy to check, but you need to actually write down some stuff, okay? Like, do this. This is why I was thinking about assigning over there, but I wanted to give you the hint. I didn't want to simply say that, check that this satisfies the requirements of Zorn's lemma. I wanted to tell you how you check that. Okay, so this is an upper bound, which is in P. So this satisfies the hypothesis of Zorn's lemma. Thus, by Zorn's lemma, there exists a maximal element in P with respect to this relation in P. Let me call that maximal element something. Let's call it M, because M for maximal. Say this well-ordered set is a maximal element. I'm saying a maximal element because there can be multiple maximal elements. So let's say that this is a maximal element in P. If it were the case that, now I claim that this set M is actually all of A. If this were not A, here's what I would do. I have some A, I have some M, and this is ordered by some relation. I don't care how it's ordered. Now, if these are not the same, I would pick some element outside. Theta, no. A, little a. If I pick some element outside and add this to M, so I'm going to add this to M. And I'm going to declare this element to be greater than all the elements in here. So I'm just going to take my ordering on M, and I am going to declare this guy to be greater than or equal to all the elements of M. Now, I have a set, I have a relation on this. This relation is a well-ordered relation on this set. You can easily check this, because how did I construct that relation? I just took the well-ordered relation on M. I just took the well-ordered relation on M and said that, okay, I'm going to declare this A to be greater than all elements of M. By doing this, you cannot create an infinite descending sequence. Okay, so you cannot just disrupt the well-ordered of this. And you can easily check that this is like transitive, anti-symmetric, and reflexive. So this is a well-ordered set. So this is a well-ordered set, which is, now if you look at this well-ordered set, this is obtained by adding one more element to the top of M. So M is an initial segment of this. M is an initial segment of this new well-ordered set. So this is related well, which is strictly greater than, maybe I should write it like this, yes, greater than, this is strictly greater than this tuple with respect to this square subset relation, okay? So this is strictly greater than this guy with respect to this relation, which contradicts maximality of this relation M, okay? Thus, M equals A. I got a contradiction, so M equals A. And so, A is well ordered by, well, this relation. Okay? So here's how we prove that every set can be well ordered. You take your set, you look at all its subsets which are well ordered by certain relations. You take these subsets which are well ordered and you put a partial ordering on them by the initial segment relation, basically. And then you show that this partial ordering satisfies the hypothesis of Zorn's lemma. So there exists that requires some thinking, not that much. And then you get, by Zorn's lemma, you get that there is a maximal element. And then you argue that if the underlying set of this well-ordered set were not all of A, then you would be able to find something which is strictly greater than this, just by adding one more element to the top. But you can't do that because this is maximal. Therefore, this is all of A, which means that I've already found a well-ordered relation on my set A. Okay? So on any set A, you can find a well-ordered relation. What? Why that set is greater than another set? Because, let's check, M is a subset of M union A. That's true. Less than or equal to M is subset of less than or equal to M union that. The only question is M an initial segment of this guy? And pictorially, this should be clear. I had M over here, which is well ordered. What I did was, I assumed that this is not all of A. I picked some element, I added this element to the top of M, okay? So, I have the order relation on N, I just add a maximal element. I just add an element which is greater than this. Well, M is a subset of this guy, and M is the set of predecessors of this new element, okay? So in this partial ordering, M is the predecessors of A. And this is an initial segment. So yeah, this means that M is an initial segment. So the third condition is also satisfied. M is an initial segment in M union the singleton A, because in this new well-ordered ring, M is literally the predecessors of A. Yes?
Would there be a case that M is the greatest element of A? And let's say that M is the greatest element of A, that we cannot be this mode.
You mean M is all of A?
No, like I'm trying to say that M might not be all of A. I mean, let's say M is the highest, like the biggest.
Sure, but if it's not all of A, then we get a contradiction.
How come you get it?
Now, I have this A, I have this subset M. This is well ordered by something. Okay, it's well ordered by this relation. Okay? So the elements of this guy are somehow well ordered. Okay, you just ordered them. Pretend that there's an element here, A. I'm going to take this element, I'm going to create a new set. The new set I'm creating is M union this singleton. And I define a new relation on this set. So this is this set, this is the second set. I'm going to define a new relation on this. I'm saying that the previous elements are ordered as is, and I define this A to be strictly greater than all these guys.
Okay, so what I was saying that, let's say that there is no such A.
Then M is all of A.
I didn't get that part. Like, why?
What do you mean?
So A can have more elements than M, and M can be the highest element of A.
What do you mean? M is a subset.
Yeah.
You mean that, okay, this is M, this is A. You don't want any elements in here.
Yes.
Which means that M is all of A. I am not picking this element with respect to the well-ordered relation. I'm saying that is there an element outside? I'm literally asking the following question. Is there an element in A minus M?
Yeah.
If there is some element,
It's not greater than M. And it's not greater than M.
sure, but this is not even comparable with all these guys. This is a relation on M. You cannot compare these elements with these elements. So I'm just defining a new relation where I can compare them. And I have to add something here actually. This is supposed to be M union A. I'm just saying that I'm defining this new element to be greater than or equal to all the elements. So I'm adding this as a maximal element. This a priori has nothing to do with these guys. Like you can't compare this with these guys. I'm defining it so that it is greater than all these guys.
Yeah, okay. Yeah.
Okay? Other questions? So, this finishes the proof of the well-ordering theorem. Okay, I have 5 minutes. Let me quickly prove the following. Now, we proved this fact, and we proved Zorn's lemma using all the axioms. Now I'm going to prove one last thing. And in this proof, I'm going to use the well-ordering theorem, this guy. I'm going to prove that for every non-empty set X, there is a function f from power set of X minus the singleton containing the empty set to X such that f of S is an element of S for all non-empty subsets. Now, if you remember one of the exercises I assigned, this statement over here is equivalent to the axiom of choice. Okay? So what I'm proving is the F axioms, all the axioms except the choice, plus this well-ordering theorem, this is called the well-ordering theorem. Well-ordering theorem implies axiom of choice. So if you assume all the axioms of ZF and this fact, then you can prove axiom of choice. Okay? So what this shows is, what this shows us the following. I'm going to prove this in a second. If I just assume axioms of ZF, we can show the following. When I assume axiom of choice, I can prove Zorn's lemma. This is the first thing I did. When I assume axiom of choice, I can prove Zorn's lemma. When I assume Zorn's lemma, I can prove the velour ring theorem. And now I'm going to show you that if I assume velour ring theorem, I can prove axiom of choice. Okay? So if we only assume axioms of ZF, all these statements are equivalent to each other. This is what I'm trying to get at. Of course, in order to finish the loop, I have to prove this, which is going to take just a couple minutes. I don't want to take too much of your time. We're going to have a break, don't worry. So, proof. By the way, that this statement is equivalent to axiom of choice is supposed to be an exercise, like from, I don't know, 6 weeks ago or something. When I introduced choice, I must have assigned this as an exercise, or at least mentioned that this is equal to the axiom of choice. The statement simply says that for any non-empty subset, there exists a choice function. Such functions are called choice functions. Okay, so here's the proof. Let X be a non-empty set. By the velour ring theorem, there is a velour relation less than or equal to x on x. I'm going to call this less than or equal to. Then the relation, okay, I'm just going to skip the details. This is not too difficult. Defined by this is non-empty, A is an S, and for all A in S, blah, 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 is this relation is, let me finish the sentence, then I'm going to explain why this is true. This is a function from this domain to x such that f of s is an element of S for non-empty subsets S. So let's understand this. So I have this non-empty set X. I have a velour relation on it because I assumed the velour ring theorem. I define a relation. This relation does the following. It relates a subset of X, a non-empty subset of X, to some element A. And this A is supposed to be in S, and it's supposed to be, apparently, the minimal element of S. What? Oh, this is S. Sure. This A is supposed to be the minimal element of S. Okay? So why does there exist such an A? Because if you take a velour set, any non-empty subset has a least element. So I am just relating every non-empty subset to its least element. This F basically chooses the least element of every S. Now look at this definition. This definition only involves this relation. So given this relation, I can define this function. That this is a function should be obvious. A is supposed to be the least element of S. For every S, you can only find a unique least element. So this is a function. And this is a function which chooses one element from each S. Like this is supposed to be the least element of S. So this does what I want. The point is the following. If I can find a well-ordered relation on a set, then I can find a choice function. How? I will simply say that for every non-empty subset, choose its least element. And that's it. Choose its least element with respect to some well-ordered relation. So once you assume that there exists a well-ordered relation on your set, you automatically get a choice function. And the existence of the choice function is equivalent to our version of the axiom of choice, which is that product of non-empty sets is non-empty. So what have we proven is in ZF, these three guys are equivalent to each other. Okay? And this statement as well. Now, I was planning to show you some applications of Zorn's lemma, but I don't have time, so let me just talk about these. And I want you to learn about these because these are pretty useful. This is why you were already familiar with Zorn's lemma before taking this lecture, and not this version of the axiom of choice that every set can be well ordered. Zorn's lemma is pretty useful to show existence of various stuff in algebra. For example, if you have a commutative ring with unity, then it has a maximal ideal. It has when I say maximal ideal, I always mean proper ideals. It has a maximal proper ideal. Why? What you do is you construct a set of all ideals, you put a partial order on them, you show that this partial order satisfies the requirements of Zorn's lemma, and then the partial order is inclusion basically, and then you say that, okay, there exists a maximal element, that maximal element is the maximal ideal you're looking for. Or you can prove that every vector space has a basis. You probably showed that every finite dimensional vector space has a basis in linear algebra, but you probably didn't show that every vector space without any restriction on the dimension has a basis. Here is how you prove it. You take your vector space, you look at the set of all linearly independent subsets of your vector space. And you say that a linearly independent subset is less than another linearly independent subset if this is a subset of this. So you basically order the linearly independent subsets by inclusion, by set inclusion, by subset relation. And then you show that this partial order satisfies the requirements of Zorn's lemma. So there exists a maximal element. That maximal element is a maximal linearly independent subset. Now, if you have a maximal linearly independent subset in a vector space, that has to be a basis. Because if it were not spanning the whole vector space, you would take an element of the span, outside the span, and add it inside, and that would be still linearly independent. Okay? So Zorn's lemma has pretty standard applications where you just take a chain, then you take the unions, and you get this big object, okay? Such as a basis or a maximal ideal. It has many applications. Indeed, let me tell you something really cool. These are all equivalent to, okay, I just told you that you can, assuming axiom of choice, you can prove that every vector space has a basis, right? I just told you that you can prove this. Here is a result from a paper in 1984. So this is this result is only 30 years old, 34. It's due to Blas. This actually implies axiom of choice. If you just assume this, if you just assume that every vector space has a basis, you can prove axiom of choice just using the axioms of ZF. So we have these. There are many equivalents of these. These are all equivalent to many, many statements. There's a single book on this, which is covering all the equivalents of an axiom of choice, which you run into in mathematical practice. So I just gave you two more equivalents, and yeah, this is another equivalent, but we don't want to prove this direction. This direction I told you how to prove And this is important. You should know why every vector space has the basis. And check out these standard applications of axiom of choice because they're going to be useful in your future courses, okay? Unfortunately, I don't have enough time to do it in this class because we need to start talking about cardinal numbers next lecture. And that's that. So let's have a 10-minute break, okay? And be back here at 48.